Alright, so I'm going to be doing a problem that combines a lot of the concepts that I teach throughout the year in physics. So it's going to combine some stuff from definitely magnetism, but also circular motion, forces, a little bit of electricity, just kind of a combination of things. So here we go. A proton travels at 1 × 10⁶ meters per second in a clockwise circular path, radius 0.1 meter. What magnetic field strength and direction is required to make this happen? All right, so let's start with this. Let's start by drawing a diagram. Here's our proton. It's going in a clockwise path, which means since it's going in a circle, its acceleration is towards the center, which means there's a force on it towards the center. All right. Let's write out some equations we know about force and also about magnetism. So we know that force is always equal to mass times acceleration. And for a circle, we also know that the acceleration is going to be v squared over r. So we know that force is going to be mv squared over r. All right? So that's one thing. In the case of a particle moving in a magnetic field, the force on that particle, the magnetic force, is going to be qvb sine theta. All right. The cool thing about this problem is whenever you have something like a charged particle moving in a circle in a magnetic field, if it's not spiraling or anything like that, you know that theta is going to be 90. So we don't even have to worry about this. Theta is equal to 90, so sine theta is equal to 1. All right? Which means that FB is just QVB. I'm going to combine these two equations. I know force is mv squared over r, and I know the only force that's acting is QVB. So I will go mv squared over r is equal to QVB. One of these v's cancels nicely, and then I can go mv over r is equal to qb. It looks like for the purposes of this problem, I want to know the magnetic field, so I will solve for b. I know these values, so I can just start plugging them in. The mass of a proton is 1.67 × 10⁻27 kilograms. The velocity of this proton, as given in the problem, is 1 × 10⁶ meters per second. The charge is going to be 1.6 × 10⁻19, and the radius is 0.1 meters. Solve all of that out, and you get that the magnetic field is 0.104 teslas. All right. So that is the strength of the magnetic field. So we have solved that much. Now we need to figure out the direction of the magnetic field. The way we are going to do this is by using our right-hand rule to figure out what direction of field we would need to get this direction of force. We know at this particular moment, while the proton is traveling in this direction, tangential to the circle, the force is towards the center of the circle here. So that means, let's see. My thumb is going to point in the direction of moving positive charge. My palm is going to kind of push in the direction of force, and my fingers will then point in the direction of the magnetic field. So let's see if I can arrange my hand like that. So my thumb is pointing in the direction of current, or moving positive charge. My palm needs to, can't do it that way. This way. Yeah, now my palm is pushing in the direction of the force. My thumb is pointed in the direction of the moving positive charge, and that makes my fingers point out of the board towards you. So that means the magnetic field needs to be pointed out of the board. Just as an aside, it doesn't really matter where I did this. If, for instance, I had chosen this moment, My palm would be pointed into the center of the circle. And in order to do that, let's see. Yeah, okay, so my thumb has to be pointed down for the moving positive charge. My thumb's pointed toward the center of the circle. The only way for me to do that is my fingers pointed out of the board. So no matter how we set this up, we're always going to get that the direction is outwards. We could say pointed out of the board. If you're writing this paper. The other option is to say that if it's a particle accelerator or something, we're probably viewing this from above, and then you could say that the direction is up. It all kind of depends on how you orient your paper and think about things. All right, so that is our circular motion magnetic field problem. Feel free to leave questions in the comments.